Okay, so as I was saying, we're on 4.4 graphs of secant and cosecant. So up first, we're going to look at the secant graph. Okay, so secant x. Notice here that the domain isn't all real numbers like its inverse. So secant is the inverse of what? Cosine, okay? Secant is the inverse of cosine. And cosine, its domain goes from negative infinity to positive infinity, right? But when you are finding the inverse of something, that means that the domain and ranges also switch, right? So our domain and range switch with some limitations. So if you see here, it says our domain is x, except x does not equal, okay? X does not equal 2n plus 1 pi over 2. So basically what that means is that on the odd numbers of n, the odd numbers of pi over 2, that's where you have an asymptote. All right, and this is because let's try that again. There we go. That's because we have asymptotes. And our asymptotes are going to be at our odd numbers of halves. So pi over 2, 3 pi over 2, 5 pi over 2, and keeps going from there, okay? So that's where your asymptotes reside. You have vertical asymptotes. Your range is from negative infinity to negative 1 and 1 to infinity. Notice that it is a bracket at 1, so it is defined at 1. Okay? So in our basic form of secant x, these are our parent function values. Instead of making a long list, these are split down the middle. So this is one pair of x. So notice here at negative pi over 2, it says it's undefined. That's because it's a vertical asymptote there. At positive pi over 2, it's undefined because there's a vertical asymptote there. Okay, and then at 3 pi over 2, undefined because we have a vertical asymptote there. But at all of our other quarter marks, the values are defined, okay? To find the values using your unit circle, you would be analyzing the reciprocals of your x values. Does that ring a bell? Okay, so secant is the inverse of cosine, which means that its trig values are the reciprocal of cosine. All right. So when we graph it, this is what we meant when we said there is a break in between. All right, everything is defined. And as you can see here at 1 and negative 1, we have those points defined, but between negative 1 and 1, there's nothing happening in between the graphs. And that's why there's that bracket in that union, because we have to pause and then resume our graph. Okay, questions about the graph? Do we see the asymptotes? We see the break, we understand the domain and the range with restrictions. Okay, so it's a discontinuous function. Okay, a discontinuous graph. That means that at several points along the way, I have to pick up my pencil, right? Or my pen to create that graph. So we call it discontinuous. The vertical asymptotes, again, happen on all the odd values of your halves, of your half of pies. There are no x-intercepts because at no point does it cross the x-axis. Its period is still 2 pi, just like cosine. The graph has no amplitude. That's because it's the concavity of it. It's going to be concave up when y is greater than 1. And so therefore, it's just going up forever, right? And it's going to be concave down when y is less than or equal to negative 1. So you don't have any max or min values. The graph is symmetrical with respect to the y-axis. So we call it even function. So it's an even function. It has that y-axis symmetry, okay? And this is all in your little handout that I gave you, so you wouldn't have to worry about writing it down, okay? Yep. Got it? All right. Next, we're going to talk about cosecant. And cosecant is the inverse of sine. Cosecant is the inverse of sine. So when we talk about sine, that's our snake, right? Snake. It's our snake. And its domain is from negative infinity to positive infinity, and its range is from -1 to 1. When you're finding the inverse of a function, its inverse means that their domain and range are going to switch, and there may be some restrictions along the way. Hence, there are restrictions along the way for this. So for us, your domain restriction occurs at n pi. What that means is that it occurs on all of your pi marks. So on every pi, there is going to be a vertical asymptote. So at every pi mark, you're going to have a vertical asymptote. By every pi mark, I mean at pi, 2 pi, 3 pi, 4 pi, 5 pi. That's where your vertical asymptotes are going to reside. And it keeps going. I'm sorry? No, just your whole pies. It happens only at your whole pies. Okay, so secant, the asymptotes are at your half a pies, right? For cosecant, it's going to be at your whole pies. Okay, and again, notice how it has that restriction at from negative infinity to -1, union 1 to infinity. So that being concaved up, above, and below situation. Okay, so when you look at our values, again, these values are coming from looking at our unit circle, correct? And finding the y values and taking their reciprocal. Yes? So at 0, 0 radians, your y value is 0, right? And if I reciprocate 0, it ends up in the denominator, which is why it's undefined. Well, yeah, because we're at 1, 0. And it just keeps going. If I was at pi over 6, that's 30 degrees, right? At 30 degrees, its y value is a half. Its reciprocal is 2, which is why cosecant is 2, okay? So using your unit circle knowledge and your unit circle, all we're doing is finding the reciprocals here. Oh, I didn't mean to cross it out. I meant to underline the undefined. As you can see here, we have the undefined points, and those are going to represent our asymptotes. Okay, any questions so far about the parent function for cosecant? Good? All right. So the graph. So again, looking at our graph, notice that our asymptotes. So we have our asymptotes at all of our pies. Yes. Notice that there's no max and min because the values go on forever to negative infinity and positive infinity. Yeah. Any questions about looking at the graph? Because there's no max and min, we'll go to here. So the graph is discontinuous because at several points, I have to lift my pencil, right? Or my pen. It's broken because of the vertical asymptotes. There are no x-intercepts because it'll never cross the x-axis. Its period is 2 pi. The pattern repeats every 2 pi. So you'll have your concave down, asymptote, concaved up, concave down, asymptote, concaved up, concave down, asymptote, concave. You get the pattern will just continue. The graph has no amplitude because there are no maximum and minimum values. And the graph is symmetric with respect to the origin. So it has that rotational symmetry, origin symmetry, which makes it a odd function. Meaning that if you have the parent function of a cosecant and you turn it upside down, it's going to look the same. Okay. So secant is an even function. It's symmetrical with the y-axis. Cosecant is an odd function. It has that origin symmetry, which means it can be rotated and viewed the same. All right. So to graph the cosecant function on a graphing calculator, you would use the identity cosecant x equals 1 over sine x. You cannot just go straight to the calculator and type in cosecant x. You have to write it in its reciprocal form. Does that make sense? Okay. And then the same thing for secant. To graph it in the calculator, you have to write it in its reciprocal form, which is 1 over cosine x. So I'm going to grab my calculator to model it. Go to y equals And I'm going to input, I want to graph cosecant. So I'm going to put in 1 divided by sine x. Okay. I'm going to go to zoom and I'm going to go to trig so that it'll be in a trig window, not all over the place. So I'm going to go to zoom 7 and it's going to put it in a trig window for me. And there it goes. Typically when we're analyzing our trig functions, especially for sine, cosine, secant, and cosecant, we're looking at it from 0 to 2 pi, what's taking place, right? So do you see how we're concaved up, asymptote, concave down, and then that pattern continues? Yes. Easy peasy. Questions, comments, or concerns so far? All right. Now we're going to graph secant. So for secant, I'm going to change my sign to a cosine. And again, it's already there, but I'm going to emphasize going to zoom and making sure you're clicking zoom trig. What this is doing is that it's putting it in an appropriate window for a trig graph. Okay. So going to zoom, pressing 7, and here we go. The graph is happening. Do you see that symmetry? There's our beautiful symmetry of our graph. Cool. Okay. Are we all comfortable putting it in the calculator? All right. And this is just showing that. See how beautiful and blessed y'all are now. This was the back of the day grainy calculator. But this is a big deal when they added this upgrade to the teacher feature where they could show you the graph and the equation at the same time. It's like a pretty legit situation happening there. All right, on the back of your handout I gave you, you should have the steps to graphing. So on the back of your handout, you have the following steps to graph. So when you're graphing a cosecant and secant graph, you want to graph y equals this. You're going to use sine as your guide. Does that make sense? When you're graphing secant, you're going to use cosine as your graph. Okay. But all reason why we say as a guide is because you're just reciprocating, right? Your X's and Y's are just, right, flipping. And so that's why we use it as a guide. Okay. You're going to go ahead and sketching your vertical asymptote. They will have equations of the form X equals K, where K is your x-intercept of the graph and the guide function. So you put in your asymptotes. You're going to sketch the graph of the desired function by drawing your typical U-shapes, branches between the adjacent asymptote. So once you define your asymptotes, you then are just going to sketch in your U-shape because you're sketching. So we're not expecting it to be perfect. And yeah, so the graph is going to be above your branches or whatever you want to call them are going to be above your restrictions, and then you're done. Okay, so let's do one together. So we have y equals 2 secant 1/2 x. Okay, so we're going to graph the reciprocal function first, which means we're going to graph cosine. So we're going to graph 2 cosine 1/2 x. Which we already know how to do, correct? Okay, so for our cosine here, it has an amplitude of 2, and my face has been doubled. Do we see that? Because at half, x's are liars. It looks like we cut it in half, but it's actually being doubled, correct? From 4.2. No one's looking at me like I'm crazy. Yeah. Okay. So that means that it's going to take us from 0 to 4 pi because our phase has been doubled. All right. After we did this, we then find our what? What do we do next? Oh, we had a cosine. We found the what? We find our 4 equal parts, yes? We just did this. So I would find the 4 equal parts, which we're all comfortable with, right? So first, cut in half, which would be at 0 to pi. Cut in half again, which would now put us at pi and 3 pi. Ringing bells for Monday and Tuesday?
I'm here to do your formal observation.
It's dual credit. All right. So then we cut it in half. Yes. All right.
Got one of the best hair in the building.
Okay. So this would be the cosine of it, right? And we all should be comfortable drawing the cosine because we did that in 4-1 and 4-2. Yes. All right. Now we're going to reciprocate everything, which means that your x's and y's are going to switch places. Yes. All right. So we're going to sketch in our vertical asymptotes, and we know that our vertical asymptotes are going to take place at where we have our zeros. This is why I wrote it. Yeah. Where the function equals 0. So everywhere that the function equals 0, those are going to be vertical asymptotes. So this is going to be a vertical asymptote. This is going to be a vertical asymptote, vertical asymptote, vertical asymptote. Yes? So everywhere that it's equal to 0, you're going to sketch in your vertical asymptotes. Are you still with me? Okay, what happened? Okay, so all we did was go through how to graph our cosine. Remember that? Were you good with that? So graph your cosine. Now, after you graph your cosine, you're going to find your asymptotes. Your asymptotes come from where your graph equals. Oh, we haven't even moved to secant. No, okay. No. Yeah. We're just drawing in the asymptotes so for the secant. Those points we just got were the. Those would have been if it was just cosine. Okay. So if it was just cosine, those would be our points. And then we find our asymptotes by where it equals 0. Those are our asymptotes. Easy? Okay. Now you're going to sketch the graph of 2 secant half by drawing your U-shaped branches between. So you're doing the reciprocal, which means that it's going to be the opposite of it. So where the parts are, that's going to be your opposite. So see right here, this is concave up. Now it's going to be concave down. This is concave down. Now it's going to be concave up. This is concave up. Now it's going to be concave down. And once you draw those branches in, you now have your secant graph. This is why 4-1 and 4-2 were really important, because if you couldn't do 4-1 and 4-2, then when we got here, we were like, oh no. And ta-da! The blue now represents our secant. Was it terrible? It wasn't terrible. Yes. Could we do it? Anyone's like, Miss, that's crazy. All right, we're going to try it again. Now we're going to do cosecant. I still have those little graph papers. You don't want them. Little graph on. Grab a couple, pass them around. One of my very great Temu purchases. Anyone needs a little graph paper for their notes? I mean, I guess no, people forget that they're there. Thank you. I'll buy more off Temu if you make me go back to that site. I've taken time away from it. All right, so now we're going to do cosecant, which means that we're going to start off with what kind of graph? We're going to start with sine, right? So we're going to graph the sine version of it. So before we graph, we should be able to talk about what's going to happen here, right? So the 3/2 is changing our what? Our amplitude. So our amplitude is being increased by 1.5, correct? By a multiple of 1.5. And then the pi/2 is changing our what? It's our shift, right? It's our phase shift, okay? The pi/2 is telling us that our phase shift is shifting to the right. So our entire function is shifting to the right, pi/2. X's are liars. It looks like it's going to the left, but it's actually going to the right. Cool. Okay, so we're gonna figure that out. Where are we at? And here we are. Amplitude means that we grew. Phase shifts is telling us that everything was shifted half to the right. So to each one of our 0, our pi over 4, pi over 2, all those things, we shift everything to the right. So a complete cycle is from pi over 2 to 5 pi over 2 because of that shift. Yes? Yeah, y'all are so smart. All right. And guess what we're going to do again? Put in those asymptotes. Okay, your asymptotes are going to be, again, at the zeros, at your x-intercepts. Those are going to be your asymptotes. So we're going to put in our asymptotes. So notice at my x-intercepts, that's where my asymptotes are going to be for my reciprocal function, my inverse function.
I just put this in the calculator, right? Like the sign, like we have the sign, find the x's.
Yeah, but you have to be able to know what the exact values are. And the calculator is going to tell you the decimal values.
But like I have in the calculator.
Yeah, but it's going to tell you the decimal value of where, and you're not going to be able to know exact. It won't tell you the values of your asymptotes.
So we're going to have to find the points.
That's why 4.1 and 4.2 were your best friends, because you got to be able to find those points. Okay. All right. Our asymptotes are drawn in, and then guess what we do have to put in our asymptotes? We're going to do our U shapes. We're going to do the opposite. So notice how we went through. This was concave down. Now it's going to be concave up. This was concaved up. Now it's going to be concave down. Concave down, concaved up, concave up. Now it's going to be concave down. And now that represents our blue. Our blue is our cosecant. Ta-da! You are now professional graphers. Training prescriptions. Good job.
Are we done?
Yeah, for the most part, unless you just want to keep going.
Can you like do brief summary of 1.3?
Yeah, for tangent and cotangent. Yeah, give me a second. All right, so
After you know how we play.
okay. So this is making sure that you're comfortable going the other way. So when I look at this graph, it's asking you what would be the best representation of it. So based on our sketches and what the graphs look like, this would be a cosecant graph. And it's cosecant because I can look at where my asymptotes are at, right? So my asymptotes are at the hole mark, but not at the hole marks, at hole marks. And it's squeezed in. So that also had to let me know that my phase had to change also, right? It expanded to 4 pi. So it's a cosecant with your phase now being from 2 pi to 4 pi. So being able to also go backwards is going to be part of being.
Yeah, I don't know how to do that.
The going backwards?
Yeah.
Okay. So when you're looking at it, you're going to have to pay attention to some of the patterns. So let me go back to these. So if you look right here, our originals. Back up, back up, back up. Okay. So if you look right here, you can see that the difference between the sine and the cosecant and secant graphs. Yes. So for cosecant, we start here. So you're going to be reflective, not reflective, rotational symmetry. So that means that there's always going to be opposites. So if I am opposites and my y-axis isn't creating a symmetry with me, that's how I know that it would be a cosecant versus a secant. Whereas secant is going to create some type of symmetry with the y-axis. You see that symmetry that's created? So it'll create some type of symmetry with the y-axis when you're following that pattern. That's thing number one to look at. You can't just look up whether it's concave up or concave down, because you can see in each phase they both are doing the same thing. And then pay attention to where your asymptotes are spaced. In reality, there is one for each.
So cosecant creates something with x-axis. I mean y-axis.
Cosecant is rotational. It's rotational. Whereas secant has the y-axis symmetry. So cosecant has rotational symmetry. Secant has the y-axis. And honestly, if all else fails, you test both out. That's what it comes down to. It's testing both out. But you can see here, you can identify how long your phase is. So your phase is 4 pi. That means that it had to be doubled, right? Which means that my B value has to be a half. So looking at things that we already know. So if this is one full cycle and it's at 4 pi, that means that my B value was doubled, which means that it would be 1/2 is going to be what B would be. So pay attention to that. And then after that, nothing else changed. My range is still at 1. So that means there was no vertical translation, right? I didn't go left or right. All I did was expand. So it's either going to be cosine or cosecant or secant. And because of this right here, this being not symmetrical with the y-axis, this lets me know that it had to be cosecant.
So I can just look at it like.
Yes, so it has that y-axis symmetry. Yes, ma'am. All right, so really quick, I wanted to show you a secant. So notice how this is symmetrical with the y-axis. You see that symmetry? That lets me know that it's going to be a secant versus a cosecant.
But it's like the equation is.
So in reality, it could be both. And so that's why we call whether it's symmetrical with the y or rotational. Yeah, because just like cosine and sine, for every cosine graph, there's technically a sine graph, a sine equation for it.
For tangent stuff, what is like.
Bye guys, have a good spring break.
Where's my paper?